Okay, shall we start? So in the first few lectures, what I did show you is how to solve a very specific problem of enumeration, which was the enumeration of maps. And what we did find out is that in order to find generating series for maps of given genus G with n mapped faces, we actually do not need much. We need to know that the generating series for genus 0 map with one mapped face is solution to an algebraic equation to which we associate what we call a spectral curve, which is a cover of P1 given by a map X, and another object, which is the genus 0 function, so generating function of genus 0 maps with two mapped faces, which we can use in order to define a symmetric bilinear differential on sigma cross sigma, the same spectral curve. Out of this data, we could write down the omega GNs, which are generating series of genus G map with n mapped faces, just by writing down such a residue formula. So it's a residue at two particular points of a bunch of factors and terms. Now, what I want to do today is to say that this is a very particular case of what is called topological recursion. Which is a formalism which in particular will apply to many other problems of enumerative geometry, saying that you want to enumerate some geometrical objects which are indexed by their genus and a number of marked points or marked faces or boundaries. And in order to enumerate these objects, you only need to know a very few minimal data, which is the data of what happened for genus 0 with one marked point or one boundary, and genus 0 with two boundaries. And once you have this data, if you can associate to it a spectral curve, then all other generating series for higher genus and higher number of marked faces or boundaries will be given by a kind of universal formula. Now, I will introduce this formalism, and I will base it in the knowledge of this formula for the case of maps. And the question I will ask now is, I forget completely about where I come from. What is the problem of enumerative geometry I wanted to solve? So the problem of combinatorics. I just remember that there are just a few minimal data I need in order to write on such a formula. And that's what I want to extract. So what is this formula? It's an inductive formula on G and N, which needs what as an input? First, it needs to know that we take some residue at a pair of very specific points, which are plus and minus 1. So in this case, there's 2 points. They were defined as being the point where dx, yeah, d0, yeah, yeah. Oh, there should be a 1 here. Yeah, no, but yeah, it's my fault. It should be a 2 to n here, 2 to n. Yeah, right. Yeah, just that. Yeah, sometimes I write on n plus 1, sometimes I write on n. Yeah. This one, z and minus z. Is it OK? Oh, no, it shouldn't have been. So it was a mistake if I did right. Because, OK, so let's go back to that. So I will tell you what is the information I need. The information I need is the position of this point where I take residue. In particular, this point are the point where dx is vanishing as a function of z, where z was a global coordinate. Is something wrong? Sorry, yeah. Yeah, it was 1 over z. Yeah, going too fast in my lecture. Yeah, it's 1 over z, sorry. Yeah, so it's 1 over z everywhere. It's not 1 over z. 1 over z, and here as well, yeah. So that's good. Yeah, so that's what I will point out. So in order to start writing down this formula, the first thing I need is the data of these 2 points, plus and minus 1. And I will try to axiomatize that. Now, indeed, what I need is these positions there, and as you're pointing out, there is this involution z goes to 1 over z. So what do have these points as, what's the specificity of these points? These are points where this map is such that dx, where x is the function which defines my cover, vanishes. So yeah, I will write it down later. So it means that locally, if I would look at, 1, 2, you think of it as the P1 downstairs, was coordinated given by x. Locally, this point dx is where, when I try to solve my equation, then I might have many points above. So in the preceding case, I had only 2 points. Now I consider the case where this equation could be of degree 3. I solve an equation of degree 3 in the second variable here. It means that for a fixed value of x, I've got 3 solutions, 3 bunches of solution. And the solution, they might coincide at some specific points, which are called branch points. And which is exactly what was defining for me this plus and minus 1. So I had an equation of degree 2 here. I did prove using Brown's lemma that actually this equation was very specific because the 2 branch of solution could meet only at 2 very specific points, which were z equals plus and minus 1. But in addition, what I know is that since I've got just simple zeros at this point for dx, it means that I've got just 2 branches of solution which meet. And so if I look around a point, a branch point which I call A1, and I take a coordinate z going to A1, in the same fiber above some x of z here, next to x of ai, I just have a pair of points, z and sigma 1 of z, which are such that x of z is equal to x of sigma 1 of z. And in the same time, sigma 1 of z goes to a1 when z goes to a1. Is there something you cannot read? Sorry? What? Here? So here I've got the point which I call A1. It's a branch point. A1. Is it OK? So now, yeah. So around this point A1, I've got an involution which exchanges the 2 copies, so the 2 branches of solution, which will merge, which will coincide at this branch point. And I call z and sigma 1 of z. There's 2 points. So if I fix z, because I've got branch point only 2 branches of solution coincide, it defines for me an involution which extends these 2 branches. And if I fix z, I call sigma 1 of z the other branch of solution which will go to the same point. So in the example we had here, the involution was indeed the one which exchanged z and 1 over z. So the 2 branch points were plus and minus 1. And when z goes to plus and minus 1, 1 over z goes to plus and minus 1 as well. Now, it was a very specific case where I just had 2 branches. So I had a polynomial of degree 2 here. So I just had 2 branches of solution. So there was no ambiguity. Wherever I would be, the other point in the fiber which would go to the same branch point would be the other solution. If I would have a polynomial of higher degree, for example 3, I could be in this case where the evolution which exchanged the 2 sheets, or the 2 branches of solution going to the point A1, might be different from the one which exchanged the 2 sheets, the 2 branches of solution going to A2. So here, around A1, the involution is the one which exchanged this branch of solution and this one, and it leaves it doesn't touch this one. On the other end, if I would be here, I keep z going there, so I've got z here. Then sigma 2 of z is not coming from the same branch as sigma 1 of z, but it's over there. And here I've got something else. OK? So actually, what I needed here was a bunch of points here and a local involution. And you see that when I think about it here, it means that when I'm next to this point where I will compute residue, I don't care about what's going on here. I just need to know what is going on around this point. And since I'm computing residue here, the only thing I need to know is what happened around the points, around the branch points, which I have. So I need to know the position of the branch point, and I need to know a local coordinate such that it gives me a good definition of this local involution. And this is what I will do in order to define what I will call a local spectral curve. So local spectral curve, it is the data of first, you need to have an integer which I will call n, which I will take strictly positive, which will tell you the number of branch points I have. And now I want to mimic what is going on here. So in order to define all these ingredients, what I need, as I was telling you, is just the knowledge of n formal disks around these points. So around the point A1, A2, up to In, if I've got n branch points. I need to know this local involution, but you see that this local involution, it just it can be obtained just by taking the following local coordinate. If you take around the branch point AI x minus x of AI, it's not a good coordinate locally because you've got the fact that dx is vanishing. But if you take the square root, and I call it zi of p, zeta I of p, if you take the square root, it's a well-defined local coordinate around a branch point AI. That's a zeta, yeah. I should always write it in the same way. So if you don't know it's zeta, no, from now on it's zeta. Now, what does the local involution do there? In this coordinate, it's very easy to write down. It just tells you that zeta I of sigma I of p is equal to the same with a minus sign for the square root. Okay. So that's why it's a pretty convenient coordinate. It's because in this coordinate, this local involution, which might be really hard, really complicated, because it's just something which exchanges the two specific solutions to a polynomial equation, just correspond to changing the sign of this local coordinate. So I will always use this variable, and I will tell you why I do that. So the yeah. Yeah. I'm always so. Yeah, but it's a very simple one. That's the one I will use all the time. That's the one I will use in order to define my local curve. So now I will tell you exactly what I want to do. So here I did fix the point I consider. I've got this local involution, and in order to be able to describe it, I will use these local coordinates. And why do I do that? It's because I compute residue. So I want to write down Taylor expansion for all the function I've got here. And this Taylor expansion, I will do it in some local coordinate. And what I do is that I'm doing Taylor expansion in this local coordinate, such that in particular, I've got this, the fact that this involution, which in this case was z goes to 1 over z, become zeta I goes to minus zeta I. Now, if I would choose another local coordinate, I would get another Taylor expansion for all my functions, but I will always work with this one, and that's the one I will use in order to define my recursion. So I want to have a general formula for expressing this equation. And what I'm saying is that I know that I'm just considering residue at branch point, and I know one way to get a kind of general coordinate which will mimic very well which will express very well this local involution, which is given by this square root. Now, if I do that, then in order to compute this residue, I just need to know the Taylor expansion of the ingredients here, which are actually only omega 02 and omega 01. And what I will do is that I will take as an input just the knowledge of the Taylor expansion of this difference expressed in this local coordinate. Okay? So the input was an integer n. Then it's the knowledge of the expression of this difference in this local coordinate, the Taylor expansion. So I just need to know for I going from 1 to n, I just need to know the knowledge of some function of, let's call it zeta of z. Yeah. So I've got n such differential, which are differential in z. Omega 01 index I as a differential in z, which is just a Taylor expansion. So it's just a gem of differential, which is holomorphic when z goes to 0. So you just write it as a series, sum over k. So we'll use my.
I is an index, or is that I choose?
Sorry? I is an index.
No, in parentheses, is that I choose z?
It's I z. No, it's not I sub z. It's an index, yeah. Sorry for the notation. Sorry? Yeah, it's just that we will have many of them. So when we've got n, things like that, it would make a lot of, it would make formulae bigger. So no, it's just an index. So you've got two things which are here, an index I and some parameters z. So I just want to write down a generic Power series in Z with positive coefficients, sum from k equals 0 to infinity, and I will use this normalization, h2k plus 1 I z to the power 2k plus 2 dz, and I put a factor 2 in front. Now here, so I just take something which is a Power series in Z with positive coefficient, but you see that I just have even powers here. Why do I do that? What I want to mimic in this formula is just this difference expanded in this local coordinate. This difference is odd when you exchange z and 1 over z, meaning that it should be odd when you apply this involution. If you would write it in this local coordinate, it means that when you exchange the argument zeta I with its conjugate with sigma I, it should change sign. And sorry? No, not an 8, a 4. No. No, a 4. 2 times 2. Why do you say 8? 4. Yeah.
You're subtracting 2 of this double, and you put 2 in front.
No, I don't subtract 2. Yeah, so this will be what I will call omega 01 I, this difference. Written with a factor 2 in front.
No, so with the 2 upstairs?
With the 2 where? Here?
Yeah, you have it outside.
So I've got the 2 here.
Yes, but it's outside of your bracket.
Yeah.
You have the 4 times this.
Yeah.
Factor of 8.
Well, 8. So I've got 2 and 2 there, because this is the difference, so it's 4. Yeah.
So the 2 is outside.
Yeah. Is it okay? So 2 times this difference, and this difference, I call it omega 0, 1, I. So the index I tells you that what I'm considering is this difference, which actually depends. So since I'm taking the difference between the value at C and the value at the point obtained by this local involution, this actually depends on the branch point which I consider. So in the previous case, in this case, it was a bit tricky because we just had a curve which was a double cover of this type. So you just had two branches of solution. So this involution was always Z goes to 1 over Z. If you're in this case, you really need to know at which branch point you are. So what I call omega 0, 1, I, Z, the index I stands for the branch point I would take here. So yeah, that's why So it's not the Z that we had before. It's a zeta. But here I'm just considering a formal series in a variable, which I could call Z or zeta. If you don't want to mix it up with this one, yeah, let's call it zeta. I was scared that if I would use zeta, that's what I planned to do. I was scared that you would say, but zeta is a function of P. So yeah, I prefer that very much, actually. OK. So that's the first part. And so the reason why I just had even porous here, it's because if you look at the product here, as a differential form, it's odd under Z goes to minus Z. And that's exactly the property I want for this difference here. Now, what do I need? Basically, what I did define up to now is the points which I consider, so it doesn't really carry any information. Just need to know the involution here, this difference, and I need to know the omega 0, 2. And I will do exactly the same thing. What I need to know actually for omega 0, 2 is not omega 0, 2 as a function of Z1 and Z2, but I need to know its stellar expansion when Z1 goes to one branch point and Z2 goes to another branch point. Because I will always compute residues here. So what I will do is know that for each I and J, yeah? Sorry? They could go to different branch points for the computation. So let's point out what happens. We will do the explicit computation later on. But remember this diagrammatic representation where I had C1, C2, C3, C4. This contributes to omega 0,4 of Z1, Z2, Z3, Z4. Here I've got dummy variable Z and another dummy variable Z prime here. When I'm computing things, I'm taking residue when Z goes to AI, residue when Z prime goes to AJ, and I'm summing over I and J, going from 1 to n in our case, of something which is associated to this graph. To each of these edges, I associate some omega 0,2. So I've got omega 0,2 of Z prime Z3, omega 0,2 of Z prime. So in the previous setup, it was 1 over Z prime Z4. I had some omega 0,2, let's say, of 1 over Z2. So these non-oriented edges, they come with a weight omega 0,2. And the oriented ones, they come with a weight which is just this kernel here, which is, let's first write on this one, the one corresponding to this part. It's the integral of omega 0,2 of Z1, and the second variable is integrated from Z to 1 over Z, divided by 2 times omega 0,1 of Z minus omega 0,1 of 1 over Z. And now I've got this part integral for omega 0 to of z prime, z and the second variable is integrated from, of z and the second variable is integrated from z prime to 1 over z prime. And I divide that by 2 times the same thing with z replaced by z prime. So is it clear? So here what I did was just write one of the contribution for omega 04. So I unfold that. I've got to go 2 steps in order to get an expression. I had this graph representation where I replace every non-oriented edge by some omega 02, each oriented edge by a kernel of this type. And then I take residue at the branch point, any branch point here. Now, let's look at this part. The weight is given by this one. And I'm computing what? Residue when z goes to ai, and residue when z prime goes to aj. So j might be different from I. So you could have to expand this omega 02 at different points. OK? And so what I need to know is not only the expansion of omega 02 when the 2 points go to the same branch point, but also when one goes to one branch point and the other one goes to another branch point. Otherwise, I wouldn't be able to write down this in local coordinate when z goes to ai and z prime goes to aj. So for omega 02, what I need to know is what happens when one variable goes to a branch point and another one goes to another one, a priori. And so I just write down the most general formula that this could take. So it depends on 2 indices, I and j, and 2 variables, z1 and z2. So it's a set of n squared differential in z1 and z2, which need to be symmetric. And with pole only on the diagonal when I is equal to j. So for I is equal to j, it might have a pole when z1 goes to z2. So it's of the form dz1, dz2 divided by z1 minus z2 squared. I should call it, sorry. We'll use the same notation, zeta. Zeta 1, zeta 2, d zeta 1, d zeta 2. And this squared, such that it has a pole when z1 goes, zeta 1 goes to zeta 2, when this corresponds to the same local coordinate, so they lie next to the same branch point. But to that, I can actually add anything which will be irregular in z1 and z2, so holomorphic. But I want it to be symmetric, so I will write it under this form, sum over k L from 0 to infinity. And I just write it in this form. So some coefficients, bklij, zeta 1 to the power k, zeta 2 to the power L, d zeta 1, d zeta 2. OK? So what I call a local spectral curve is just its data. And what I want to mimic is what happened when I've got No. No, in the definition. So in this one, the omega 01 appears always as a difference. So you only need to have the odd part. For omega 02, it's not the case, because omega 02, you see, it appears inside, in which case you will just need the odd part, or even part, actually. But it appears also there. So when I make an expansion of this as a function of z2, when z2 goes to a branch point, I might also have the even part. OK? Yeah. So what I wanted to mimic is something which will have n branch point, and I just need to know the expansion of my initial data, which is this omega 0,1 and omega 0,2, around the branch point. And what I'm doing is that, in addition, I write down the expansion in what would be the local coordinate given by the square root. Yeah. Delta ij. Yeah. So there is no I equals 0 or j equals 0. There is no particular point. So now I will map it back to the general case. But the idea is the following. When I've got the I here, it means that zeta, the associated zeta here, can be thought as a local coordinate around AI. So here, if I've got I different from j, it means that this one is variable next to AI, and this one is variable next to aj. And I write it in local coordinate. What I want is something which will have pole on the diagonal. So when the 2 points come together, if they are not in the same patch of coordinates, if they are close to 2 different points, they cannot be together, so there won't be any pole on the diagonal. The only thing which might happen is if I is equal to j, meaning that they correspond to the same local coordinate, then I will have this type of pole. Okay? Yeah. No. So that's why I call it local, because the data that you need are actually just formal disks around your point. So these are just some germ. One way to think about it is to say that these are generating functions just for bookkeeping. So no, a priori, so my point is that the recursion, I will be able to define it in this way. Now, if I do that, I will have some properties. But no, if I want it to come from the Taylor expansion of some function or differential which are defined on a compact Riemann surface, this will put a lot of constraint on them. And if I have these constraints which are satisfied, then the topological recursion will produce some omega gn which will have some additional properties. So that's the minimalistic setup. So you can think about it in this way. One way to think about it is to say that you're just given some branch point, A1, A2, up to AN. And some formal disk around these points. With some local coordinate, which I call zeta. I mean, I use the same symbol here. So you can think of it as a very specific case for this, saying that sigma here, the cover, is not connected. It's not compact. It's just a union, disconnected union, disjoint union of n disk. And my cover is just that here I've got a map to another disk, which is above 0. So theta is a local coordinate, and the map is just theta squared. Now the question is, can I see them as coming from cover of P1? So here, I was just giving you a formal thing just next to the branch point. Now, in some cases, one way to generate this local spectral curve is to start from what we might call a global spectral curve. So the question is the following one. OK, I gave you this setup, and what I will tell you is how to define some omega gn just out of this data. But in some sense, there is an infinite number of initial data I have to give you. So the question is, in which cases, in which nice cases, can I produce such structure? So I gave you an example in the past lectures. And how to produce so-called curves. And this was an example of starting from a global curve. where you don't need much, you don't need that much information. So what do I call a global curve? It is a cover of, let's say, C with a map X, as before. So one way to think about it, if you want to have something which is easy to understand, is the data. So you can think of some algebraic curve, so the data of a polynomial into variable, such that sigma is just given by the set of solution to this equation, so the pair X and Y of solution. And the data of some omega 0, 1 of P, which is a one form on sigma. So if I've got this part, so this cover, then I look for the zeros of the X. If I've got n solution, this is what corresponds to this n small disk. So if I want to produce a local curve which has n as an index, then I need to produce such a cover of C which has n branch points. Now I have given you some omega 1, which is a one form on sigma. I call it P because it's a point on a curve. Yeah. But yeah, it's just a point. And so what will be interesting to me here will be the expansion of this omega 1 around the branch point, AI. So around AI, I write omega 1 of P, and I just Taylor expand it in a very specific local coordinate, which is the one I gave you earlier. Write it as 2 sum over k from 0. Write it as sum over k from 0 to infinity of h2k plus 1, hk z to the power k plus 1, dz. Yeah, fits with this notation. Yeah, no, sorry, I will. Yeah. So I expand it in a local coordinate, which is this zeta I, which I defined before. So it's zeta I of P. So for now, it's only omega 1. Thank you. It's zeta I of P. So I'm given X, this cover, this map. So it defines for me a local coordinate zeta I around the branch point AI. And I just write omega 1 as a Taylor series expansion in this coordinate. So I just write it under this form. Now, if I would look at omega 1 of P minus omega 1 of the other variable, which goes to the same branch point AI, write the difference, it will be a series which has only odd terms here. It comes with a 2. And this is what will give me the data of this bunch of omega 1 I theta. OK? So that's one way to get the HK. So you see that HK, I've got an infinite number of them. HIK, sorry. I've got an infinite number of them for each branch point. But from this case, it just comes from the knowledge of a one form on sigma, which in many cases will be much easier to get. And indeed, it has less information. You don't have this infinite number of information. No? Yeah? Yeah. So you put k is equal to, OK, call it L. L equals 2k plus 1. Yeah, I did it right. You call this 2k plus 1. 2k plus 1 is 2k plus 2. Is it OK? If you want, I can call it L. Yeah. So it means that from this data, I was able to give you this part and this part. Okay? Now, what about the omega 02? It will be the data of some bidifferential, so omega 02, which is a symmetric two form on sigma cross sigma. So it's a one form in P1, where P1 belongs to sigma, and a one form in P2, where P2 belongs to sigma. It is symmetric under the exchange of P1 and P2. And it has only one pole on the diagonal, so when P1 goes to P2. And this pole is such that omega 02 of P1, P2 behaves like dz of P1, dz of P2 divided by z of P1 minus z of P2 squared plus some regular part. So what I require is that it's a symmetric two form on sigma cross sigma, and it has only one pole, and it's on the diagonal. And in addition, in any local coordinate, which I call z here, it takes this form. So it's a double pole without residue, with a factor 1 here. So in particular, I could write it in the local coordinate zeta I for an arbitrary I. It will give me this part. And the regular part, I can expand it in local coordinates. And it gives me this infinite series here, where I've got I is equal to j. Now, if I would expand it when P1 goes to AI and P2 goes to A2, I'm away from the diagonal, so I don't have any pole. So I just have the regular part. And so it gives me exactly the same formula, type of formula, but without this part. Okay? Now, if the curve sigma has genus 0, this is unique. And it means that if sigma is genus 0, you can have a rational parametrization, a global parametrization, exactly as we did in the previous case. The coordinate z, which we did find, was a coordinate defined globally on the curve, and it was coming from the fact that sigma had genus 0. So if sigma has genus 0, in this coordinate, you can always write your omega 02 as this polar part without any irregular part here. And it's unique. So if sigma has genus 0, it's unique. If sigma doesn't have genus 0, what you can do always is take any omega 02 of P1, P2, and you add to this sum over alpha, beta, let's call it du alpha of P1, kappa alpha beta, du beta of P2, which is built in the following way. So omega 02 is an arbitrary omega 02 which satisfies that. And I just shift it by a symmetric product. So kappa is a symmetric matrix, a symmetric product of holomorphic one form on sigma, meaning that this series here, where alpha and beta range from 1 to g, is a symmetric holomorphic form on sigma cross sigma, so it doesn't have any pole. So I'm preserving exactly this property. So if the genus of my curve here is non-vanishing, I always have this, this choice which I can make for the omega 02. Okay? So no, omega 02 is not holomorphic, it's meromorphic. Yeah, sorry. Yeah, so the space of such form. So how can you prove that? You just take the difference between two guys, you get something which is holomorphic and symmetric. So holomorphic means that you can write it in this way, and symmetric means that you've got a symmetric matrix here. So you know the space of admissible omega 02 in this case. You see, it's far from being infinite dimensional. Whereas here I've got an infinite number of data associated to each pair of branch points. So now if I've got this data, you see that starting from this sigma with a bunch of branch points, A1, A2, A3, and a map to, let's say to C, then I can kind of zoom in, and this is this zooming in, which gives me the local data I need here. Okay? Done? Sorry? What do you call parameterized? The data of X?
Just this.
Yeah.
Because what you actually care about.
Yeah, sure. Yeah. But in some sense, it's a bit related to the choice of X. I could take some, no, but I agree. I could, zeta is equal to some function of zeta I, which is odd. Yeah. Yeah, you could, yeah, indeed, yeah, yeah. Yeah. Is it true that you get fewer? No, because the way I will, I mean, that's what I didn't define what I will compute there. So what I will write on is a formula for the omega GNs now. So these were my initial data. I write it in this local coordinate. Now I will write some omega GN out of this data. What you can, so the formula for omega GN depends on the coordinate I did choose here. Now if you would expand it, if you would make another choice, you could find another formula for omega GN such that they coincide just by this change of local variable. Yeah, I agree. Yeah. But you're not losing any, so the parameter space is the same. No. Yeah. Yeah. Yeah, but what I'm saying is that the formulas that I will get for the omega GN in this new coordinate will be another formula. So the formula, sorry? Yeah, yeah. But so it doesn't, it will not decrease the number of data I need. There is no equivalence. So it's just the expansion of the same function in different coordinates. Here I've got an infinite number of coordinates. So you've got a map from an infinite number of coordinates to another infinite number of coordinates. You've got a linear map, which makes you change a variable, right? Yeah? Yeah? Yeah. In your yeah. Yeah. But what do you mean? Yeah. No, I don't agree. What? Yeah, I could take another coordinate, I agree, but okay, I didn't get it. Yeah, okay. This is right, and actually, in some sense, I will do it explicitly, I hope, tomorrow. Yeah, okay. No, I didn't get your point. So what you were saying is that there is a particular coordinate which would be the one with all the HK vanishing except the first one, and I could take that as a coordinate. Yeah. 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 Yeah, sure. Okay, what time is it? Yeah. So maybe now I can write down the formula for the omega GNs. So you see the drawback of this local point of view is that you've got an infinite number of coordinates, and you also have to carry all these additional indices, which tells you which branch points you consider for your for your expansion. So you see that for each variable here, I had an index associated which corresponds to which branch point I choose. And this is the same thing I will do for the topological recursion. So if you start from a local curve, which is the data of n omega 0, 1 I. What did I call it? Omega 0, 1 of zeta I and omega 0, 2 of zeta 1 I zeta 2j. Then I will produce some omega gns. So before, these were differential forms in n variables, zeta 1, zeta 2, to zeta small n. Now I've got to say to which local coordinates each zeta I correspond to. So it depends on indices I1, I2, In, where each of the ij's belongs to the set 1 to n, capital N. So this will be gem of multilinear n form in zeta 1 to zeta n, which I define in the following way. I just take the sum over all possible values of I, and for each of them, I compute the residue when zeta goes to 0. And what do? I do as before. I take my omega 0, 2, where the first variable is the first one here. So it's zeta 1. And it was associated to I1. And I've got the second variable, which will be the zeta here, which is associated to the I in my sum. And I integrate it from zeta to minus zeta. So I integrate it from one point to its image under this local involution. Since I'm working with coordinate where this involution is just the exchange of sign, it treats in this way. And I divide by 2 times omega 0, 1 of zeta with the index I. And yeah. Sorry? This one? Yeah. No. No. Just, I've got an index here, which I sum over. So let's call it J if you prefer, not to have any confusion. No, it will not play a difference, except that maybe there won't be any confusion. So you sum over J, any possible value of J, and you sum over them. So this J doesn't have anything to do with the I1, I2, In. OK? Sorry? Is there any issues there? It's just that, OK. It seems, seems that it works. So yeah, I mean, it's just a summation variable. It has nothing to do with the ij here. OK? And you multiply that by omega g minus 1 n plus 1 of, and zeta is always associated to this j. So first variable, you take zeta. Second variable, you take its image under the local involution. And then you take all the other variables here, except for the first one, I2, theta 2, up to in theta n, plus, and then you've got the sum of disconnected elements. So sum over stable terms of G1 plus G2 is equal to G. A disconnected union B is equal to 2 to n. And you've got some omega G1 cardinal of A plus 1 of I theta. And here I will use the same notation as last week, IA theta A, where this stands for all the ij theta j where j belongs to the set A. And this times the same thing for G2 and B. And you just act with the local involution. Yep. So that's the formula, and it mimics exactly what you had before here. And we will talk about it after the break, I think. So we'll have a 5-minute break. OK, so maybe we can start the second part of the talk. So first, yeah, sorry. I did write I here. It should be a J with this notation. And so how does it go? You've got the sum over J of residue. So it's a sum over n residue. And for each residue, you take the residue of this big product, the product of this part, times this sum, where each of them depend on the index J. For further needs, I will introduce a notation, which is this one. If you consider this part, so what is it? Something which depends on Z1 and Z, zeta 1 and Z, and zeta. And two indices, I1 and J. That's what I will call sometime the recursion kernel. The first observation is that, watch out, it's not symmetric in the exchange of zeta and Z1. So what do I call it recursion kernel? Because this formula tells you that if you want to compute omega Gn, with n variable here, you just take a sum of residue at n points of this recursion kernel times a sum here, which is a sum of terms which have simpler topology, meaning that if you would work with lexicographic order with respect to G and N, this will be known by induction, just starting from the data of omega 0, 2. OK? So that's the so-called topological recursion formula, and it produces some n form, which depend on n indices ranging from 1 to n. Sorry? Yeah. Yeah, that's what I will draw here. The first thing I want, yeah, maybe I will go to the graphical representation first. So if you look at it, the formula is the same. And you had the formula here, which was a sum of two residues. We had a recursion kernel here, which was an integral of omega 0, 2 divided by different of omega, times another factor, which is exactly the same as here. The only difference here is that the involution around +1 and -1 was the same. So we didn't have to introduce this J index here. Yeah. And this is that's actually a puzzle, because when you want to generate topological recursion or you want to generalize them, the simplest case you would look at are cases where your curve, you start from a global curve, which is defined by a polynomial of degree 2. If you've got a polynomial of degree 2, it means that typically you've got a cover of this type, and the involution, exchanging these two branches and these ones, is always the same one. So what you will find out is that you will find a formula where you will not see explicitly the dependence on this index J. And so sometimes when you work with these cases, you've got some formula which look very nice, but cannot be generalized, because you did hide this involution. But now let's go to the graphical representation. So I want to represent once again this omega gn in this way. So a genus G blob with variable θ1, θ2, θn on legs. But now I've got an additional index, I, for each of them. I1 θ1, I2 θ2. So I've got pairs In θn associated to each of these legs. And the formula tells me that, one way to represent this formula is to say, I will represent my K of I1 J C1 at θ1 θ. I will represent it by an oriented edge going from θ1 I1 and going to a vertex which is labeled by J θ. Okay? So I've got my sum over J from 1 to n, and I represent this vertex. I1 θ1 J θ. And as before, I will have to say which leg is associated to zeta and which leg is associated to minus zeta. And I will do that by marking one of the legs. And I say that the weight of this graph is equal to this graph obtained by degeneration, where I still have my legs I2 θ2 In θn plus sum over J from 1 to n, sum over stable contributions, G1 plus G2 is equal to G, A union B is equal to 2 to n. And I do exactly the same thing. I've got my recursion kernel, I1 θ1, J θ with one marked leg. And now I've got G1 on one side and G2 on the other side. A set of legs whose indices are I8 zeta A, and another set which is of type IB theta b. So it's exactly the same representation as before, except that in the preceding case, I didn't worry about labeling the vertex with a branch point. And here I do it explicitly. So yeah, now in order to compute the weight of such a graph, when I've got a trivalent vertex, I replace it by this k here. When I've got it with an oriented edge. Any blob like that, I replace it by some omega gn I computed before. And I just compute the residue when zeta goes to 0. Now maybe we can start unfolding this procedure. Yeah. So what is the first one? The first function we can compute? It's omega 0,3 of I1 theta 1, I2 theta 2, I3 theta 3. By definition, it's a sum over j from 1 to n of residues when theta goes to 0. So the representation is the following one. You've got I1 theta 1, and here you've got your trivalent vertex, and you attach to it omega 0,2s, which should be blobs of genus 0 here, but as last time, I do not represent these blobs. These are just lines. So I2 theta 2 with marking here, I3 theta 3, plus another contribution, which is just obtained by the exchange of 2 and 3. So now I will write the contribution. So I'm just taking a residue, and I sum over j. I'm taking a residue when theta goes to 0 of k I1 j theta 1 theta. And here I just have omega 0,2 of, so the first one, zeta 2, where zeta is associated to j and zeta 2 is associated to I2. Of theta 2 j, theta j, I2 theta 2 times omega 0,2 of j minus theta I3 theta 3 plus the same thing with 2 and 3 exchange. Now you've got an explicit formula for omega 0,2 k in the as Taylor series around zeta equals 0. So you just plug it in and you get a formula for your omega 0,3. First remark, just look at this formula. Does it look symmetric under the exchange of zeta 1, zeta 2, zeta 3? Yeah? OK. I mean, to me, it doesn't look at all symmetric. So it's symmetric under the exchange of 2 and 3. But Z1 plays a very different role here. And that's the reason why I've got this representation, which is not at all symmetric. Now a theorem. For all G and N, omega Gn of zeta 1, I1, In, zeta n is symmetric. Under the exchange of its arguments. So if you exchange ij zeta j with ik zeta k, it is symmetric. What? Yeah. Any exchange of them, so you can take any permutation of these sets. If you look at the definition of the omega Jn, this is something which is really not obvious. In the preceding case, in the case of maps, since this omega Gn were generating series for some numbers which were symmetric, then we were expecting this symmetry. But here, from the definition, it was really not obvious. Now, I will not prove it because it would take some time, but I can give you an intuition of the proof. And you will see the use of this graphical representation. Yeah, here it is symmetric. I didn't say it. So BKL IJ here is symmetric under the exchange. So that's one of the constraints. So yeah, by definition, this is true for G equals 0, N equals 1, and N equals 2. And now you want to prove it by induction for arbitrary G and N. And how would you prove that? So you want to prove it by induction, and you want to prove that this guy is fully symmetric. So as you see, I did put the I1, zeta 1 on the left side on purpose because by the definition, it plays a very specific role. So it's not symmetric compared to the other one. The definition is symmetric under the exchange of the other legs. Now the question is, can I permute these two legs? And what I will do is that I will compare that with the same one, where I've got I2 zeta 2, I1 zeta 1, I3 zeta 3, IN zeta n. And for doing that, I will just follow the definitions, this topological recursion definition, and I will just do two steps. The first one tells me that I've got this sum of J of object like this. So I've got the first contribution, which is this one. So I've got I1 zeta 1. G minus 1 here. I2 zeta 2. IN zeta n. Plus sum over J, sum over stable terms of something disconnected, where zeta 2 belongs to one of the sets here. So I used to write it as I add zeta A. IB zeta B. And sum over G1, G2. So where A and B now give a partition of 3 to n into 2 subsets. So that's the first step. And zeta 1, I mean, the index 1 was playing a particular role. Now, I will use my induction hypothesis saying that everything which is simpler, so which is involved in the recursion, is symmetric. So for example, this one is symmetric under the exchange of all the legs. So I can choose whichever leg I want in order to write on my recursion. And I will do it by starting from there. So I still have this sum over j from 1 to n. Ah, sorry, yeah. I've got my j theta here. J theta. And now I write on the recursion for this one. So I start from there, put some arrow, oriented edge, I2 theta 2, and I just write on the recursion. So I've got the trivalent vertex here with another index, let me call it k, and I will make a sum from k from 1 to n as well. And now I've got all possible elements as before. So for example, I could have something like that. Could have, when I shrink this cycle, I could have something which remains connected, but which has one genus, one pole less. So genus 1 in this case. And I3 theta 3, IN theta n. So that's one of the contributions. So here I've got an index k theta prime, and I will have to take residue when theta prime goes to 0. But because I did some ordering, remember that this, I will take residue in theta before taking residue in theta prime. And I've got a bunch of other terms. So I could have things which will be disconnected. From this one, j theta, k theta prime, plus the same kind of thing, so I could have something like that. Where I still have my j theta, k theta prime. And remember that this is related to I1 theta 1, and these two I2 theta 2. Now, if I would have done exactly the same thing by exchanging the role of I1 of theta 1 and theta 2, I would get exactly the same sum over graphs. Now, the only thing which changes when I say that I start from with theta 1 and then with theta 2 is to say that I first have to take residue when theta prime goes to 0, and then residue when theta goes to 0. So I will have, in this case, residue first when theta prime goes to 0, residue when theta goes to 0. And I've got a sum over j, k from 1 to n of functions which are just the weight associated to this graph. So this is what I would get if I would take first this one and this one. And I want to compare it with what would happen if I would do the other round, exchanging 1 and 2. So I would compute the same thing, but just taking residue when z prime goes to 0, residue when z goes to 0, of exactly the same thing. And the question is whether this vanishes or not. Now you see, you've got many terms which you've got to take into account, but they can be represented graphically. Now the point is that, something I didn't mention before, what you can check is that the omega gn, except for the case where g equals 0 and equal to, have poles only when z goes to 0. So one of the arguments goes to 0. So there is no pole when z1 goes to z2, except for omega 0,2. Meaning that what I've got here is something which doesn't have any pole when z goes to z prime, except in some very particular cases. Meaning that you don't have any pole when z goes to z prime means that you can exchange your integration contour. So this is vanishing except for a few cases, which are the cases where here I've got some omega 0, 2. In the case where you've got omega 0, 2 here, you can explicitly move your integration contour and compute the contribution, and you will find out that this difference vanishes. So a priori, that's a tricky procedure. You would have to do a lot of computation, but with this graphical representation, you've got a good knowledge of what is involved. And you know that you've got this kind of formula where this is the same differentials here. You know its poles, that you know that in general it doesn't have any pole when z goes to z prime, such that this difference vanishes, except for some few cases which you can enumerate. And you can compute explicitly the residues. Yeah, that's the idea behind this theorem. So if you want to play with that, it's a very good exercise to get in touch with this recursion. And once again, the computations which are involved are only residue at 0, and you've got everything which is given under the form of Taylor series around 0, so the computations are quite easy. Is it OK? Did you get the proof, more or less? Because this symmetry is one of the most important property of this omega Gn, which is not at all obvious from the beginning. So let me state a few other properties. No. But it is the same thing. So you assume that omega 0, 2 is symmetric. It's the same procedure, but you will have only terms which will contribute. And so you've got to make the computation, move your integration contour. So we've seen one property, which is the symmetry. Another one is the homogeneity. So Don was saying that actually the only important thing is the omega 0, 1 was the leading coefficient. And actually, even that can be rescaled. So you wonder what happens if you take some omega I zeta. So you take a bunch of them for I equals 1 to n. And you replace it by lambda omega 0, 1 I zeta, where lambda is an arbitrary non-vanishing complex number. What does it do to the omega Gn's? Actually, when you have the formula in front of you, it's not very complicated to see what's going on. Before I give you the result, I will give you the proof, which is the following one. Where does omega 0, 1 zeta I appear in the recursion? It appears actually only at one place. It appears in the kernel K. So under this, since the kernel K of I1 J zeta 1 zeta is the integral of omega 0, 2 divided by omega 0, 1. Then it goes to lambda minus 1. The same thing. It is just rescaled. Now, from the graphical representation, this K, which is the only thing which is changed when you make this rescaling, it appears only when you've got these oriented edges. And actually, you've got such an oriented edges for edge only for each trivalent vertex in your graph. So what does it mean? It means that omega Gn will just be rescaled by lambda to the power minus the number of trivalent vertices. And this you can count. It's lambda to the power 2g minus 2 plus n omega gn of I1 theta 1 in theta n. So if you change omega 0,1 by multiplying it by some lambda, your omega gn, they will just be multiplied by lambda to the power 2g minus 2 plus n. So they are homogeneous. You can think of them as being homogeneous in omega 0,1 of this degree. Yeah? Because for getting a good expression, it's better in terms of intersection numbers. Yeah, I agree. So this factor of half, I could have got rid of it just by a change of lambda. But you could see it from the beginning, just 2 times this omega 0,1. But now when I will have later on, when I will want an interpretation of this, this as generating series of numbers, intersection number on the moduli space of curve, 2 is the good one. Yeah. That's one of the good things. Yeah. Now, by the way, yeah, I had the power of 2, and actually I could change the sign. I could put a minus sign as well, which would enter in the lambda. And yeah, I want to warn you, in the literature, if you read about topological recursion, you might have different definition, some with some minus sign, some also with a factor of 2 or not. But most of them can be reabsorbed in this rescaling. What time is it? Okay. So a few more properties. Which one did I forget? Yeah. Now, there is another question we can ask, which is the following one. Let's assume we know omega gn plus 1. Can we get omega gn? Yeah. So it works as well. G equals 0 and equals 2. Gives you lambda to the power 0. It's not changed, because it doesn't know anything about omega 0,1. It's an independent data. So yeah, you've got homogeneity of omega 0,2. Okay, so can we do that? So for example, in the case of maps that we had in the past lecture, it would be the following question. If I know how many surfaces of genus G, maps of genus G with n plus 1 marked faces, can I get out of this data the number of genus G maps with n marked faces? Meaning, can I forget about one of the markings? And the answer is that you've got an equation which we can call for Dilaton equation. Or you can think of it as a forgetting equation or recapping equation, which is the following one. If you take omega g n plus 1, j theta, theta 1, I1, in theta n, you multiply by phi j of zeta, where phi j of zeta is a function of zeta, such that its differential is equal to omega 0,1 of zeta j. So you've got a function of, you've got a differential in zeta, zeta 1, zeta n, and you take the residue once again when zeta goes to 0. Sum over j from 1 to n. divide by, and here I don't want to have the factor wrong, 2g minus 2 plus n. Then this gives you omega gn of zeta 1 I1 in zeta n. For 2g minus 2 plus n strictly positive. So I will not prove this. Yeah. So yeah, d phi j zeta. So phi j zeta is a function of zeta. Its differential is omega 0, 1 of zeta j. So one of my initial data. Sorry? It has only one j here. Yeah. So this is the initial data, your series in zeta. And if you take the d phi, it's given by that. So you could wonder whether this depends on some choice of primitive, but it doesn't. And the result is that you've got this formula. So this formula tells you how to forget about one of your variables. And now you see that the topological recursion, which I define some omega g n for n at least equal to 1. I want to have differential form. And this motivates the definition for omega g0 by saying, OK, I just take this formula for n equals 0. I get something here. And I will call it omega g0. I will call omega g0 for g at least equal to 2. Just the result of this formula. So it's 1 over 2g minus 2, sum over j from 1 to n. Residue when zeta goes to 0 of phi j of zeta omega g1 of zeta j. So I don't have any variable of type zeta. It's not a differential form in zeta anymore. You can think of it as a number a priori. But another way to think about it is to say, when I do all these recursions, these topological recursions, this depend on my initial data, this omega 0,1 and omega 0,2. So actually, this omega g0 is a function of the hk's and bkl, which I give you as input. And so they play the role of omega gn with n equal to 0, meaning that they play the role of generating series of maps without any marked phase. And actually, in the case of maps, which we studied last time, I didn't want to study this case. This is exactly what it does. OK. Yeah, I think I will stop here for the properties. So up to now, what did I do today? I started from the formula for the enumeration of maps. I tried to translate it in a more general setup, forgetting about this map interpretation, and tried to generalize it for arbitrary cover of this type. And I produced some omega gn, and I gave you some properties that this omega gn satisfy. Now, OK, these are nice objects. But the very good thing about them is that you can really use them in different setups. So let's say the history of the subject is that Bertrand Hénard defined a formula for the enumeration of maps, which is basically what I showed you last time, which at the end of the day is a formula of this type. Then we decided to study. I started my PhD, and my PhD was about the Ising model on random surfaces. And so Bertrand Hénard's plan was to say, OK, can we use the techniques that he had found there in order to solve this model? So what is this model? It's very similar to the problems that we had before. So before, we were enumerating maps, which you can think of as discrete surfaces with a weight. So I was associating a weight tk to each k gone. Now you can ask the same problem by saying, OK, I want to enumerate polygonalization of surfaces, but now I allow two types of polygons, so some black polygon and some white polygon and some black polygon. And I put different weights. So for example, here, if I've got 4 gons, so a square of white color, I would give it a weight T4. And here I've got a square which is of the other color, and I give it a weight T4 twiddle, which is completely independent, different data. And I gave a weight also for the edges between two polygons of the same color, let's say black, between two polygons of the same white color, or for the edges between polygons of different color. And I put different weight for these different type of edges. Now, I can define some generating series in the same way as I did before. Compute some T, G, K1, Kn, which is a sum of a genus G bicolored map with n boundaries. And where now on the boundary, I put some constraint, which is the following one. Remember that what I call a boundary is a marked face. So here I always represent the marked face here outside. Now this marked face could be of color black or white. And let's say that I will put all the boundaries or all the marked face of the same color, let's say white. So I can build some numbers as before and sum over all k's and produce the same generating series. Call it W Gn of x1, xn. So it's a problem which is very similar to the previous one, but now you've got some more decoration of on your maps. And now question, can I compute this WGN? The answer is yes. And in particular, you start from the fact that if you study W10, you can show by using some loop equation, which are similar to a Tutte equation, that W01 of x is solution to an equation, polynomial equation in two variables. But before, it was a polynomial of degree 2 in the second variable. Now it's a polynomial of degree d, a d twiddle, let's say, where d twiddle is the maximal number of edges that a black polygon can have. So I did associate to this Ising model in this way. We can associate a curve. And now what you can prove is that if you apply the topological recursion to this curve, then you produce exactly the WGN. So it's another application which is exactly in the same setup as before, enumeration of discrete surfaces, but now we have some decoration. So one way to think about it is that we make, again, a sum over maps, but now the weight of each map is different. Now, actually, there are many other interesting models of this type which exist. So you can wonder what would happen if I would also allow to draw loops and give a weight to polygons which are crossed by a loop. You've got a huge family of such problems. And for a large class of this problem, I know there have been many works on that, then you can associate a curve, which might not be a polynomial of this type, but you can associate at least a local curve such that the WGN, which are, again, generating series of this type, are computed by the topological recursion. So I showed you one example completely explicitly, but the same structure appears in many problems of enumeration of, let's say, random surfaces which are built by polygons, where you put some decoration on them. What I will show you tomorrow are examples where, instead of making a sum over maps, which are discrete surfaces, you compute some integral over the moduli space of Riemann surfaces with respect to some measure. And this is where many new applications appear. And yeah, I think I will stop here today.